Oh geez, I don't even know what you're gonna. I haven't even prepared.
Oh,
it's gonna be great.
That's fine.
Off the cuff.
That's actually. I'm not really sure what Dawn wants me to do, but that's kind of what I want. I want more casual.
Okay.
Because this way it's not, hi, I'm a professor and I do all this. It's like, hey, here's my personality. I'm a real person. Love me.
Me. Love me or leave me. Gotta love me. And my headphones on. That's how you know it's really me. These beats, so they're like disintegrating. So every time I listen to my headphones, there's like little bits of black flake that are like coming off. So I just make sure there's like nothing on my ears. But that's actually how you normally see me, with headphones on and scuttling about campus.
Okay. Let's see. Jessica. Well, just Jessica came and talked to Professor Dowling like a week or so ago.
With Colville and I.
Okay, that's what I was going to ask. Were y'all involved in that conversation at all?
Yes, so I think she interviewed John in the beginning, and then he kind of, we were to meet him there because we were going to go with her down to the lab so she can get some action shots. Unfortunately, Professor Corbett wasn't available, but he still had us come in at the end just so she could ask us like a couple of questions. So, yeah.
Okay.
And I think she's going to reschedule the lab visit whenever Professor Corbett is down there. Because John himself doesn't have the quantum science group is mainly theorists. So Dr. Corbett is an experimentalist, and he has a lab, but it's more with gravitational waves. And then Omar has just arrived, and he's a new experimentalist, and he's building his lab. So to get some kind of live lab action shots, we had to use Professor Corbett's, but he wasn't available. So we'll reschedule that in the near future.
Okay. And that may end up being me. Because I don't think the rest of them really like doing video.
It's probably color in there.
Oh, cool.
Oh, no, it's not. No, it's not. I thought it was him. What's up?
Hi.
Welcome back.
All right, there we go.
I just thought they may be going back and forth.
Oh, that's fine.
In and out.
Again, casual.
Okay, cool.
Okay, we'll keep right.
No, you guys are fine. Turn it up. Turn the music up. No, I'm joking.
We'll probably turn the movie scene on.
Right? Ding.
Okay, so the big project with the quantum internet and such, are you going to be involved with that? Or are you doing something else?
As it stands right now, I'm not sure. I'll probably more than likely be involved with that because of the fact that, again, as I mentioned, Omar is building his lab right now, and a lot of the things that he's building will be working kind of with the quantum networks, the quantum LiDAR. Really, it's more quantum LiDAR. The networks, they're experimentalists working on that. John, they're doing more of the theory here, but I wouldn't be surprised if, because I'm an experimentalist, he and Omar kind of work some things out to work on that. If I don't work with Omar and I work with Professor Corbett, then I'll be working with him on the quantum metrology, the quantum measurement, making the LIGO sensors more sensitive to gravitational waves. So it just depends on where John sends me, but he knows I'm interested in the quantum communications and quantum teleportation and all that. That's something that got me interested in physics, and so I'm pretty sure he's going to throw me in there eventually.
Okay, there's two things I've got questions about. You were saying quantum LiDAR and quantum teleportation. If you could explain those a little more?
Yes, so I can't, because I'm learning about them myself. So with the quantum teleportation is really something about, you know, which the fastest way that we could transfer information. And the fastest way you can do it is via teleportation. That it doesn't have to go through space and noise and all that. So, you know, the fastest way to send something is as close to the speed of light as you can get it. And so, you know, we send things on photons or in photon states, entangled states. And so that's how you can kind of, you know, send your information. But all I know is that we use entangled states, which is, you know, what they always call something spooky, but basically it is what we call a superposition of states. So just imagine if you have something that can point up and then it can point down. In classical mechanics, or in the macroscopic world that we know, it could only point up or it could only point down. In quantum mechanics is a field that is non-deterministic, so you cannot say 100% sure it's up, 100% sure it's down. it is in a superposition of all possible states of up and down that it can be in simultaneously. And therein lies the kind of advantage of exploiting things, exploiting the quantum mechanical nature of things, is that you actually can store information in all of those many states that, a spin, as we would call it, could be in, or the polarization of a photon. In this lab, we use quantum optics, so I'll say a photon. In my previous research experience, we were actually trapping ions, so we were using atoms, and so you talk about spin. But yeah, that's about the best I could do right now. The quantum LiDAR, I have no idea, man. I feel bad, because it's like I want to explain it to you, but I'm learning myself. So this is the research that I'll be reading papers on, and kind of gaining more knowledge about. Okay. The buzz right now is that the Chinese, of course, have sent their own. They have actually, they have the record now. I think it's 1,600 either miles or kilometers. I'm not sure, but they hold the record for quantum teleporting information to and from a satellite orbiting in space.
Okay, now.
So they've actually built the satellite and they've made the quantum teleportation protocol.
When you're saying teleportation, are you saying that because it's photons and it's traveling at the speed of light, or is it actually something's here and it just rematerializes?
Right. So teleportation and that. So quantum teleportation involves a lot of that. So for example, in quantum mechanics, we have something that's called the no cloning theorem. So you cannot clone or copy a quantum system. So in effect, you're actually, let's say you have a photon on Earth, you're actually destroying that photon, and that information is being rematerialized in a state in another photon somewhere else. So you're destroying the information here, and it's actually appearing here. So it's very much like the Beam Me Up Scotty.
That's what it sounds like you're describing.
It is. It's like Beam Me Up. It's very similar to Beam Me Up Scotty in Star Trek, where something actually is destroyed here and then rematerializes elsewhere. So one set of information materializes, but it's something similar to that.
Okay, now you were also talking about up and down, and then it could be both. And that sounded like Schrodinger's cat almost. Like you're not sure what state it's in.
Yeah. So the Schrodinger's cat. So basically, so for the Schrodinger's cat, yeah, you're basically talking about. Let's say you have two containers. Mm-hmm. And this is the example that John always gives. So in one container you have, some kind of destructive acid. Okay. Or in fact, no, let's take that back. Let's take that way back. Let's say in one container you have an atom, a radioactive atom that can decay or not decay. And in the other container you have a cat. Both the containers are closed. But the one thing you do know is that if the atom decays, or if the radioactive material decays, you kill the cat. So, and the cat right now, because you have not seen it, it is technically in a state of alive and dead, is what we say. You don't know though, because until you actually open the box and observe it, you don't know what's happening to the cat. So it is in both states at the same time. And so that's what we mean by like entanglement. Or I'm sorry, that's what we mean by it's in a superposition state of alive and dead at the same time. If you were to open the radioactive material, and let's say you look into it and the radioactive material has decayed, you automatically know the state of the cat without having to open the box and look at the cat. So those two things are entangled, meaning that, so let me be clear. In the two containers you have the radioactive material and the cat. The cat is alive or dead, you don't know. It's really alive and dead at the same time. Because it can be in both positions. That is a superposition. That's what we call that. So it can be in both of them at the same time. The entanglement comes into play because if you actually observe something in one container, you automatically know the status of the other thing without having to observe that thing. Okay. So it's almost like you can look at it without looking at it. And that's the kind of premise behind entanglement.
So would that be like the photon is destroyed, so you know the information's at the other end now?
Yes. So therefore, if you prepare both of your systems and you send a photon up to the satellite, and you have one down here, and you know the polarization with which you set this photon, as it evolves in time and changes, or comes to some position, you automatically know the state of the one up on the satellite without having to look at it. So that's the entanglement that they have together. Okay. And it doesn't matter how far you move the photons apart. So you can have, the example is always given, you can have a photon here on Earth, one on Alpha Centauri, millions of light years away. And as soon as you measure this one, you automatically know the state of that one. So that gives rise to, does the information travel faster than the speed of light? Because you can't have anything that goes, per Einstein, you can't have anything that goes, faster than the speed of light. And come to find out, it does not travel faster than the speed of light because you need classical channels. You need classical communication to actually determine what the state is once you actually measure it here. So, or shall I say, you need classical information to measure the state here. John's gonna kill me. I'm trying to
okay,
get
but
this
wait.
Straight.
If you say you were at Alpha Centauri,
right,
and you had someone else here,
right,
is it that, say I'm on Alpha Centauri and I get the information,
right,
and we both have synchronized timing or whatever,
right,
is it not traveling faster than the speed of light,
that
or is it?
Information that you get has to come via a classical channel.
Okay.
So that's why. So we say that the state itself can travel at the speed of light, but you actually gathering the information, physically seeing like, I have this information now, that has to go over a classical channel, and that does not travel at the speed of light.
Okay.
Yes.
So it's not possible for it to go faster.
There's a third channel part, no.
And so y'all haven't found some
non-linear
folds in time, space, sort of.
Not yet. Still trying to build the. What is it? I need to watch Doctor
Stargate.
The Start is it? The
the TARDIS.
The
TARDIS.
Thank you. Still trying to build the TARDIS. So.
Okay. There's a new doctor, lady.
Listen.
Jodie Whittaker.
Listen, Jodie. Yep, I'm gonna say Jodie. So we'll see. But yeah, so you have to have what we call a class. So it's not all quantum. You have to have a classical channel to see, to interpret, if you will, the information, and that is what kind of makes the laws of relativity work, if you will.
Okay, so this is not limited by like line of sight, or like you would have to bounce it off a satellite. Like say you're in China, I'm here.
Right.
Are we bouncing off a satellite? Or are we just going from the two things?
So what's going on? So from the satellite, they're actually sending photon pairs. They're called Einstein-Podolsky-Rosen, or EPR pairs. And these are entangled photon pairs that get sent. And to be clear, they're sent down in China right now. I'll come back to that in a minute. So, perhaps a pair is sent to Beijing, another pair is sent to Shanghai, another pair is sent to like China or something like that. But regardless, you have these EPR pairs that connect networks on the ground. And so they give you kind of virtual hack-proof communication along that communication line from the satellite, because you can tell if someone is eavesdropping on that system. And this is again per, well this has, I'll explain that as well, because one of the biggest things with the satellite and quantum information is that, or quantum cryptography, is that it is virtually unhackable. So I'll come to that. But for right now, yes, they actually have photon pairs that they're sending from the satellite. And that's where you're getting your kind of quantum encryption from.
Okay, when you say a pair, we're two locations. We each get one of the pair, or you get a pair and I get a pair? What are you saying with that?
That is a good
Because that kind of leads to the hacking thing.
No, both of the photons go to the same. So the pair is for the entanglement to happen.
Okay.
So you need to have the entanglement.
So it would be your photon being destroyed here and recreated here, or whatever the word is you'd use.
No, so you have two photons that are entangled to give you the channel, if you will, to which you actually get
like the Schrodinger's cat
your
thing.
encrypted messages over.
Okay.
Right. So
So that's the channel, and that stays open as long as the connection exists?
As long as the connection exists.
Okay.
So through the satellite up to that.
Now when you say network, is my computer to the satellite a network, or is it like a LAN where I've got a dozen computers and that's my network?
If I'm not mistaken, I think it's a LAN. So that's what we're working on now. So the satellite is sitting. So this is all still ongoing research right now. Okay. So the Chinese they actually have little places on the ground. And because this is a question that I asked, is it one-to-one? Do you have to have, how many pairs can come out of the satellite? Is it just one pair? How many satellites do you have to have? Is it 20 billion satellites in orbit, or do we only need to have 1 or 2 satellites in orbit?
Yeah, that all makes sense. Those are good questions.
Right, because if you can only have a pair going here and a pair going here, so these are all open, ongoing questions. So I just want to preface, by saying that. And again, I'm still learning about this myself. But if I'm not mistaken, it's the EPR pair. So the EPR pair is actually what gives you the entanglements. Those photons come out in pairs. Okay. And then you're on the ground at your, at whatever kind of system that you're using, whatever quantum system you're using, quantum computer, what have you, in the future. And you're communicating, you're sending your messages via satellite. So let's say they always use Alice and Bob. So let's say Alice is here in Shanghai and Bob is here in
Pyongyang.
What'd you say?
Pyongyang.
In Pyongyang.
North Korea.
First of all, we're keeping it in China.
Oh, okay.
Keeping it in China for right now, just for right now, because you were asking even about China to America. I'm going to get on that. So for right now, we're in China. So from Beijing to Shanghai. Okay. And so Alice, wants to send a message to Bob. Right. She wants it to be encrypted. She doesn't want it to be eavesdropped on. And so she has to have her own quantum channel. And then Bob has to have his own quantum channel.
And that's each a pair.
And it's in each, it's 2 EPR pairs.
Okay.
Exactly. Okay. And then the classical part comes in when they have to actually kind of connect and make sure that the message she sent is being interpreted correctly. And all that hilarity ensues. And that's where all the quantum stuff that I'm learning about comes from. So now to the Pyongyang, to the Americas. So governments are not too trusting with other countries. And if the Chinese, the protocol that they use, the users on the ground may not know the kind of encryption that's going on, but the satellite knows everything. And so if you are in control of that satellite, which is a Chinese satellite, would other world governments trust, being able to send their information over this satellite, or send their information to this satellite and trust that their information is going to be protected? So that is what is called the BB84 protocol, what the Chinese are using right now, where users know nothing but the satellite knows it all. There's an Eckert 91 protocol that the satellite doesn't know anything, the users don't know anything. So effectively you have secure communication.
It's like a double blind.
But if you want to think of it like that, double blind, no one knows anything. And so if that becomes a realization on a broad scale, then yes, any country could use the satellite and they could be ensured that their information is secure.
Okay, now back to Alice and Bob.
Yes.
You're talking about it being unhackable. Yes. Say I'm Alice, or I'm Alice.
Right.
And I'm on my network here, and there's like 10 of us.
Right.
Are we all on this one pair, so when it's unhackable and gets shut down, this entire network goes dark? Or how does that work?
This is an open question, because that goes back to how many pairs can come out of a satellite. If I'm not mistaken, I think it's just 2. So that means that only, Shanghai and let's say the next, province over can be on this one satellite, and then therein lies like their land. Okay. Might actually be a WAN. I'm not sure. But
well, if it's that big, it'd probably be a WAN.
Yeah, that's like probably a WAN.
If it's outside a building.
You're right. So, and so then multiple users can get on there, and then to answer the question, if the network is interrupted, first of all, we have to define, the information has already been sent through noise. So it's notwithstanding air, atmospheric effects, all the stuff, the satellite, the orbit. I'm assuming that they've taken care of all that, and that you wouldn't actually have network disturbances unless the satellite itself has some, trouble or something like that.